something for the first time probably ever in your guys' entire math careers. And we're going to be talking about geometric sequences and series today. So we're first going to start off with geometric sequences. So many of you are like, I have no idea even what that is. So I'll just give you a brief idea about what a sequence is. So a geometric sequence is built by multiplying each term by a constant. So when I say sequence, I'm just talking about a sequence of numbers. We just have a bunch of numbers in a row, and they are going to, each term is going to change by a certain number that you're multiplying by. So you'll just sit and multiply each term by a certain constant, and that's going to make up your geometric sequence. And so with that being said, if you think about it, let's say that we're multiplying by 3, for example. Let's say that that constant we're multiplying is by 3. So we have some number, we multiply it by 3. We now have a new number. We multiply that by 3. Now we have a new number. We multiply that by 3. We now have a new number. Well, that is just getting exponentially larger and larger, right? So we know what exponential functions look like. So really, geometric sequences are exponential functions, but it's just going to be written in a different form. Okay, so to find the ratio means division, to find what you're multiplying by each time to get from one term to the next. You're going to find the ratio. Ratio means division, guys. And to find that, you'll take the term and divide it by the previous term. So you'll just take this term, divide it by this term. Then you'll move on. Take this term, divide it by this term. So you're just going to be dividing terms to find out what you're multiplying by. So let's just do number 1 on the worksheet together. We're going to do number 1. So you can go ahead and look at your worksheet, work through this one on the worksheet if you want to. But here's our first example. So it says, determine if this sequence is geometric. If so, find the common ratio. So notice when I said geometric sequence, I just had a sequence of numbers. So we have the numbers 3, 9, 27, and 81. This one's pretty easy to see. What is the common ratio? Like, what are we multiplying by each time to get from one term to the next? Good. We're multiplying by 3. Well, you're right. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So our common ratio is 3, so this is geometric because we were multiplying by 3 every single time to get from one term to the next. So you would say yes, and the ratio, so it is geometric because we were multiplying by 3 every single time. So yes, and then your ratio was equal to 3. So that would be your final answer. Now, not all of these will be as obvious as this one on what your ratio is. So you could have found the ratio like this. Now watch, because you're going to be dealing with decimals, you're not going to be able to just see all the time what you're multiplying by. So you could have found it by doing 81 divided by 27. So this term divided by the term before it, which is equal to 3. Then you would check the next one. 27 divided by 9, which is equal to 3. Now 27 was the term before 9, and then 9 divided by 3 as well. So 9 divided by 3 is equal to 3. Now you'll want to know how to do it that way because, like I said, not every single sequence will be as obvious as this one. You guys all understand how you can find this algebraically by dividing using a common ratio. Does everybody see what I did there? You took the term before a term and divided it by the term that came before it. Okay, so now you're going to do problems 2 through 9, but I just wanted to say one quick thing. We're dealing with geometric sequences today. There are such things as arithmetic sequences, so that would be adding. So an example of an arithmetic sequence would be something like 2, 4, 6, 8, 10. Now notice in this sequence, it's not geometric because we're not multiplying by a certain constant. We're adding a constant each time. We were adding 2, adding 2, adding 2, adding 2. So this would be an arithmetic sequence. We're skipping that unit because we don't have time to cover it, but it goes hand in hand with geometric sequences. Geometric just means what you're multiplying by. So multiplying versus adding, okay? So ready, set, go. Do problems 2 through 9. Okay, so as you can see, a sequence is made up of a bunch of numbers that we just took a number, a constant, and we multiplied it by it each time. So really, if you think about it, a sequence can go on forever, right? We can just continue to multiply by, let's say that it was 3. Well, we can just continue to multiply by 3, and our sequence can get larger and larger, and we can just keep doing this forever. But as you can tell from all of those problems on 1 through 9, it has a starting point. So it's going to give you a specific starting point. Does everybody see on number 1 how the starting point is 3? On number 2, the starting point is 4. On number 3, the starting point is 4, once again. So they're all going to, yes, they can go on forever, but they are going to have a starting point. Okay? So it's going to be denoted by a sub 1. So this means the first term. So a sub 1 means this is the first term of our sequence. So just so you know, notation here, a sub 1 means the first term of the sequence. So that's our first term. So looking at number 10 below, just real quick, number 10 on your worksheet is the same as well. We're going to go through number 10. It says find the 10th term, so we're going to do that next. But first of all, just looking at this one, what would our a sub 1 be? 2, our first term. It's that simple. A sub 1, our first term is 2. Okay, sweet. So we could do this many ways. I'm going to go through it the long way really quick. It's not super long, but I'm going to show you one way of doing this. So it says find the 10th term. Well, looking at this, what are we multiplying by? What's our ratio? What's our R? Like, what's our common ratio? What are we multiplying by each time to get from one number in the sequence to the next? The ratio is 2. Now, you know that 2 times 2 is 4. 4 times 2 is 8. So you're right, our ratio is 2. Or you could have done it algebraically. You could have done 8 divided by 4 is equal to 2. And then 4 divided by 2 is equal to 2. So we know it's 2. Okay, sweet. So we could find the 10th term, not too bad in this one. So we have 2, 4, 8. Let's just keep multiplying by 2 each time. So times by 2 is 16, times by 2 is 32, times by 2 is 64, times by 2 is 128, times by 2 is 256, times by 2 is 512, and times by 2 is 1024. Let's see if that's enough. So this was a sub 1, that means our first term, a sub 2, our second term, 3, 4, 5, 6, 7, 8, 9, and 10. So we went to our 10th term. We found the 10th term of this sequence. We could keep going if we wanted, but we're stopping here. Now, this wasn't too bad, right? Because I just said find the 10th term, so it wasn't too bad. But what if I would have said to you, find the 150th term? Yikes, that would take forever, right? You'd be sitting here all day. So we would not want to do that. And I can promise you on the test, I'm going to do one like that to make sure that you don't use this method. So I'm going to give you a formula to be able to find any term of any given sequence. And that's what I'm going to show you next. So there's actually a formula you're going to use to find any term of a sequence. And here it is. So it's called the explicit formula. And that's exactly, I have the test in my office. I was reading it, and it straight up says, write an explicit formula for this sequence. So you need to, when you see the word explicit formula, you need to know that it's this formula. So this is a to the n, so this means any term. So a to the n, we can plug in, we can find any term, because we can put in if you want to find the 10th term, instead of n, we're putting in a 10. So a sub n is equal to a sub 1, which means the first term, times by the common ratio, so times by r, raised to the n minus 1. So once again, a sub n means whatever term we want to find. And then a1 is the first term, r is the common ratio, what we're multiplying by each time, and then n is the number of terms that we're trying to find here. So does anybody have any questions on what this is? Okay, so we're going to do the last problem with this formula. So on number 10 instead, we're going to use this formula. And our number 10 was 2, 4, and 8, comma, dot, dot, dot. Okay. So first of all, we want to find we were asked to find the 10th term. Okay, so we were asked to find the 10th term. So our n in this one is going to be 10. We're trying to find the 10th term. So really we're trying to find a sub 10, which makes sense. We know that a sub 1 means the first term. So now we want to find a sub 10 means the 10th term. So a sub 10 is equal to a sub 1. A sub 1 is just the first term of the sequence, which we already found was 2, which is pretty obvious. You just look. That is the first term. And then we found out our common ratio by doing 8 divided by 4, which is 2, and 4 divided by 2, which is 2. So r was 2, and that's all we need to know. So let's just substitute that in to our formula now. So a sub 10 is equal to a sub 1, which is 2, times by our common ratio, which is 2, I'm plugging it into the formula, raised to the n minus 1. n minus 1. So now piece by piece, we're just going to simplify this. A sub 10 is equal to 2 times by 2 raised to the 10 minus 1 is 9. And then from here, you'll just type it into your calculator. But you just got to type it in correctly because you've got to make sure you don't do 2 times 2, which is 4, raised to the 9th. No. This 2 was not raised to the 9th power. If you multiply it in first and then raise it to the 9th power, you were saying that this 2 right here was also raised to the 9th power. So you got to type it in like this. 2 times by parentheses 2, only that 2 raised to the 9th power. And if you do that correctly, you should get, now we did it the long way, so we already know our answer is 1,024. So practice typing that into your calculator and make sure you get the right answer. So if I was saying find the 100th term, wouldn't this formula be 10 times easier than actually multiplying out 100 terms worth of stuff? Yeah, this was quick. Not bad at all, right? This stuff's not hard, you guys. It's just plugging it into the formula and putting it in your calculator correctly. So there's our answer. Any questions? So make sure you use that formula and you have it in your head. Okay, the explicit formula is this formula and it allows me to find any term in any given sequence. Okay? And yes, for the SAGE test, you'll have to have this memorized. I'm not going to give it to you. You'll have to remember it. So if you need to put a star by it in your notes, do that. Okay? So now you're going to do problems 11 through 18. So we're not learning anything new right now. I just want to make sure I go through number 19 with you to make sure that you understand exactly what's expected of you and just kind of make sure you're good to go for these ones. So it says, write an explicit formula for each sequence and then generate the first 5 terms and then find the 13th term. So first of all, we're going to write the explicit formula. This is on a test exactly. You would say, okay, I know the explicit formula. I'm going to write it down. It is a sub n is equal to a sub 1, meaning the first term, times by our ratio raised to the n minus 1. So we know we need to have a sub 1, we need to have the ratio, and then the n minus 1, it just depends on what term we're trying to find. N is the term that we're trying to find. So the first thing we're doing is writing an explicit formula in general for this particular sequence. So we're given that a sub 1 is 3, and we're given that our ratio is -2. So let's plug it into our explicit formula. Now, since it says write an explicit formula, you're going to leave it general for now. So a sub n, leave it n, because it's telling us to write an explicit formula that will work for any term we want to find. So a sub n is equal to a sub 1, which is 3, times by our ratio, so times by r, which is -2, raised to the n minus 1. Now, does everybody see how this is the general explicit formula? So we could plug in any number here and find any term in this sequence. So now let's go to the next thing here. We're done with the first thing. It says, then generate the first 5 terms. Well, be careful with this one because the first 5 terms, it doesn't necessarily start by plugging in a 1 or a 0. You don't know exactly, but we do know that the first term is 3, right? Is our first term 3? Okay, sweet. And then we're multiplying by what each time? We're multiplying by what each time? -2. So I'm just going to go through, that's not that many, 5. I'm just going to multiply by -2 each time. Does that make sense? So 3 times by -2, -6, guys. And then times by -2 is 12. Times by -2 is -24. And then times by -2 is positive 48. Very good. And I just did it this way because that was the easiest. We could, though, however, after that, well, let's just do it this way. This is the easiest way. It doesn't take much brain power. So this is a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. So we went to 5 terms, and we're done with the second part. You don't need to put the a sub 1 and through a sub 5 in there. I was just showing you that this is 5 terms. Now we're asked to find the 13th term. So once again, I'm not going to go through and multiply this out to 13 terms. That will take forever. Let's just use our explicit formula. That's why we have it. So we're doing a sub 13 is equal to a sub 1. We're just plugging in here. So 3 times by -2 raised to the, we're plugging in 13 because we're trying to find the 13th term. So 13 minus 1. So really we have a sub 13 is equal to 3 times by -2 raised to the 13 minus 1 is 12. And then from there you're plugging in your calculator correctly. So a sub 13, meaning our 13th term, is going to be I got positive, I got a positive, so check your signs again. Make sure you're putting things in parentheses, especially that -2. So 12,288. So practice typing that in to make sure you can get that correct. So our three answers were check, check, and check. So, all right, so now you can do problems 20 through 26. Any questions on this? Okay, so we were just dealing with geometric sequences. So we just had a sequence of numbers. So we had a bunch of numbers that were just separated by a comma, a sequence of numbers, and then to get from one term to the next, we were multiplying by a common ratio. So now we're going to shift gears and go into geometric series. So series versus sequences. Now people kind of combine the ideas and get them confused, but you got to really keep them separate in your head. Sequence is just a sequence of numbers. You can use the explicit formula to find any term in a sequence. Now we're in series. So the difference between a geometric series and sequence is that a series is not going to be separated by commas, but it's going to be separated by addition signs. So we're going to be finding sums of geometric numbers. So it is going to have the same idea. It is going to be, each term is going to have a common ratio, but instead of a comma, it's going to have an addition sign. So we're going to be finding the sum of a bunch of numbers that have a geometric pattern. Okay? So what you do need to understand, though, is there's a difference between finite geometric series and infinite geometric series. So a finite geometric series has a specific endpoint. So for example, you can't see it because my thing's covering it up, but I had plus 96 at the end here. So notice finite means you can see the end of the series. So looking at this geometric series, notice our ratio is 2. We're multiplying by 2 each time to get from one term to the next. Once again, it's a series because it's instead of having a comma right here, it's an addition sign. So we could add up all these numbers. 3 plus 6 plus 12 plus 24 plus ... that means whatever's in between, plus 96. Well, the reason this one's finite, you guys, is because you can see the end. It's telling you to add up this sum up to 96. Does that make sense? Starting at 3, add up all those numbers up to 96, and you can stop at 96, so you can see the end. Infinite means, well, think about infinity. That goes on forever and ever, right? Infinity is like huge. We can't really comprehend exactly what infinity means. It's so far one direction and the next, so it goes on forever. So really with infinite series, you can't see the end. So it doesn't have a specific endpoint. So for example, 3 plus 6 plus 12 plus 24 plus ... that means continuing forever. We don't know the end. Okay? So does everybody understand the difference between finite series and infinite? Finite, you can see the end. Infinite, you have no idea what the end is. Okay, sweet. So with that being said, if we wanted to, we could go through and add these up. So let's say, okay, we know our R is 2, we're going up to 96, so we could do 3 plus 6 plus 12 plus 24, we're just finding the sum, plus, and we're multiplying by 2, so plus 48, multiplying by 2, plus 96, and then that's where we are ended. So we could add this up, 3 plus 6 plus 12 plus 24 plus 48 plus 96, and there's our answer, there's our sum. There's the end, so we knew the start to end, we could add those up and find the sum. But infinite, we wouldn't know where to stop, so I'm going to get to that next. So we're going to do number 1. We're going to do number 1 on your worksheet together. Here we go. So it says, find the sum of a finite series. Now remember, finite means you can see the end. So looking at number 1 on your worksheet, it's 40 plus 20 plus 10 plus ... But it tells us it wants us to add this up to the 10th term. So n is equal to 10, that means up to the 10th term. So I'm going to do this the long way, as I call it, just like I showed you the last time so that you guys can see what's going on here, and then I'm going to give you a better way to do this. Okay, a quicker way. So if you want to just watch this part, that's fine. And then I will give you the formula. So up to 10 terms. Well, first of all, we need to know what we're multiplying by to get from one term to the next. So what's our R? You're dividing by 2. Or R is always multiplied by, so what would be the same thing as dividing by 2? 0.5. Multiplying by 0.5 or multiplying by 1/2. Now you guys, a lot of you can't just see that, so let me show you algebraically how to figure that out. Just like with sequences, you can take the first term, a term in head, and divide it by the term that came before it. So 10 divided by 20 is 1/2. Then you can do 20 divided by 40, which is 1/2. Does everybody see how I could find 1/2 algebraically? Okay, so we know our ratio is 1/2. So let's go through and find 10 terms worth of stuff and then add it up. So we're going to have 40 plus 20 plus 10 times by 1/2 is 5, times by 1/2 is 2.5, and continuing on, so plus 1.25, divide that, multiply that by 1/2 or divide it by 2, so plus 0.625, we're not to 10 terms yet, so multiply that by 1/2 and that would be 0.3125 plus 0.15625 plus multiply that by 1/2, 0.078125. Now that was not too bad. Once again, it was kind of annoying. That's 10 terms out. Now we can sum that up, add it up. And if you do add that up, you're going to get 79.921875. Now that wasn't too bad, but what if I would have said r is equal to 100? Would we have wanted to keep doing this? No, it was getting really annoying even with just 10 terms. So now I'm going to give you the formula to be able to find the sum of any finite being the key, finite series. Here we go. So are you ready for the formula? Okay, so here's the formula for finding the sum of a finite, meaning you can see the end of a geometric series. So S of n, that means sum up to whatever term you want to do. So n is the number of terms you want to do. So the sum of however many terms is equal to a sub 1. A sub 1, just like in the last problem, is just the start of the series, the very first term of the series, times by 1 minus r. R is the common ratio, raised to the n, all over 1 minus r. So with this one, you've got to be just really careful when plugging things in to your calculator, especially because r raised to the n, only r is raised to the n. And then you've got to almost put, you do have to put this in parentheses in the calculator as well, or else it will calculate it wrong. So we're going to do number 1 with this formula. So number 1 was 40, 20, 10, but then it did say stop at the 10th term. So we can find, we know the end here, we're talking the 10th term. So we found the common ratio as well. It was 1/2. And then our first term of this series is a sub 1 is what? 40. So now we'll just plug it into the formula here. So S of n happens to be 10 because we want the sum up to 10 terms. So S of 10 is equal to a sub 1, which is 40, times by 1 minus r, so 1 minus 1/2, raised to the nth power, so n was 10, all over 1 minus r, so 1 minus 1/2. And I'm going to make sure when I type it into my calculator, you have to put this in parentheses because it is 1 minus 1/2. It's all over 1 minus 1/2, so the 1 minus 1/2 you've got to do first. So now if you type it into your calculator, you need to practice typing it in because this one's the trickiest one to type in. Make sure you throw parentheses around your 1/2, raising it to the 10, closing your parentheses, divided by all of this, but you've got to do 1 minus 1/2 altogether. So our sum up to 10 terms is equal to, practice typing it into your calculator. You better get the same thing we got in the last example by doing it the long way. But we're not going to use the long way from now on because it's a lot quicker to just do it this way and use our formula. So you should get 79.921875, just like we got before. So our sum up to 10 terms of this finite geometric series is 79.921875. Any questions on this one? Any questions on this one? Okay. So I'm going to have you do 2 through 6, and then I'm going to bring you back to do 7. I was going to show you one more, but I'll have you do 2 through 6 first, and then I'll bring you back to show you before you do 7A and B. So ready, set, go. 2 through 6. So you've seen that geometric series, we've just been adding up a sequence of numbers, right? Series means addition, adding up the sequence of numbers. So we've been dealing with finite series, meaning we can see the end, so we have a start to end. Well, you're going to see this sigma notation. Well, it's the same thing that you've just been doing. It's written in sigma notation, though. So look up here at this example. It's not this, it's similar to the two you're going to do, but look up here so you know how this works. So this is a sum sign, a summation sign. So we've been finding the sum, that means addition, right, of a bunch of numbers. So this sigma just means, it seriously just means the sum of. So it's the same thing as having a bunch of addition signs. So we're finding the sum of this function. So we did see that these were exponential functions, right? So notice this is just an exponential function. So we're going to find the sum of this function. Now it doesn't have to be exponential, but we're going to find the sum of this function. And our start is at n is equal to 0, and it goes to 5. So our ending is 5. So the starting term is when we plug in a 0 for n, and our end is plugging in a 5. So does that make sense of why it's finite? Because we see that the starting is that n is equal to 0, and then the end is 5. Okay? So this is still a finite series, but the problem is a lot of people confuse, how do I explain this? Let's find the sum. Now we could do this the long way by plugging in a 0, then plugging in a 1, then plugging in a 2, then plugging in a 3, then plugging in a 4, then plugging in a 5, and then adding up those terms, but that's going to take us a lot longer than just using the formula. But I do need to make a point. Now this is where the most common error comes in. How many terms do we really have here? Good, we have 6. Now think about why. If we plug in 0, I'm just going to put stars, I'm not going to actually do it. If we plug in 0 into this, we're going to get a number, correct? So we'd get some number if we plug in 0, right everybody? I'm putting a star saying we'd get a number. Okay, well if we plug in 1 into n, we'd get a number. If we plug in 2 into n, we'd get a number. If we plug in 3 into n, we'd get a number. If we plug in 4 into n, we'd get some number. If we plug in 5, which is our stopping point, we'd get some number. How many terms is that actually? 6, right? So you've got to make sure you plug in n is equal to 6 because there's actually 6 terms in this one. We didn't start at 1, we started at 0. So 0 accounted for 1. 0 plus 5 more, so that would be 1 plus 5 would be 6. Does everybody understand how n is equal to 6 in this one? So we're actually adding up 6 terms. Does everybody understand that? Yes? Okay. Sweet. So now we'll just use our formula. So the sum up to a certain number is equal to, and this is the formula for a finite series. S of n is equal to a sub 1 times by 1 minus r raised to the n all over 1 minus r. So let's use this formula instead of actually doing those out. We could though, but that would take forever, especially what if I said up to 100 here. So we're going to use our formula. So we need a sub 1. Well, what's the starting of a sub 1 is the first term. So how would we find the first term? How would we find the first term? You know this. It's not hard, guys. Well, yes, it is 3. And how did you get that? How do you know it's 3? You're right.
I don't know, but you got to write down on your forehead and keep blinking red. Sorry.
Anybody? Give it a shot, guys. Think about it. Why is 3 the starting of our series here? Because you what? You're right. It is the beginning of the equation, but how algebraically did you get it? What's our first n that we're plugging in? Okay, I'll show you. So to find a sub 1, you've got to look at your first term here, which is n is equal to 0, guys. Everybody watch, because you didn't understand this, so watch. N is equal to 0 was the start of our series, right? So plug that into our function, and that would give you the first term. So we would have 3 times by 1/2 raised to the 0 power. What's anything raised to the 0 power? 1. So really we have 3 times by 1, which is 3. So a sub 1 is 3. Does everybody understand that?
So you just enter 0?
Yes, because that is the first term of, that is the first thing we're plugging in, yes. So if we wanted to find the second term, we would plug in 1. If we want, does that make sense, everybody? Okay, is everybody okay with that? Okay, so a sub 1 is 3. What's our ratio in this one? What are we multiplying by each time to get from one term to the next? 1/2, so r is 1/2. And then we can now plug it into our formula. So s up to, we got to make sure we put in 6 because there was 1, 2, 3, 4, 5, 6 because we were going from 0, 1, 2, 3, 4, 5, which is 6 total. So s of 6, the sum up to 6 terms, is equal to a sub 1, which is 3, times by 1 minus r is 1/2. I'm going to put it in parentheses, 1/2, raised to the n was 6, so raised to the 6, close your parentheses, all over 1 minus r, so I'm going to put that in parentheses as well, 1 minus 1/2, and then you'll actually calculate this on the calculator. So s, the sum up to 6 terms, is equal to, if you type this in correctly, you should get, let's see here, if you type it in correctly, you should practice it, you should get 5.90625. Does everybody understand how to find the first term? Plug in what you're starting at. So what if this was n is equal to 1? What if this was n was equal to 1? Then we would have plugged in a 1, and our first term would have been 3 times by 1/2, right? Everybody, do you all understand that? Okay, because you got to pay attention to that on, like, it's not always going to be just easy, like, look at it and say 3. Every time, plug it in to make sure. Okay, now you'll do 7a and b, because they're the same as this. Just to find a sub 1, plug it in, your first term, or the first n, and then that's your first term. The common ratio is what you're multiplying by each time to get from one term to the next. I had a really good question I want to point out. Notice in this one we had n, and in this one we had n minus 1. Well, don't let that throw you off. The formula is still just with an n. The formula is what the formula is. The only thing that will change is when you're trying to figure out your first term. So that's the only thing that's going to change, trying to figure out your first term. Because what if n would have been 0 in this one? To find your first term, you would have plugged in a 0, so we would have had 5 times by negative 2 raised to the 0 minus 1. So really we would have had 5 times by negative 2 raised to the negative 1. Does that make sense? That n minus 1 only affects your first term, your function. Because that n minus 1 is just part of the function here. But still, when you're plugging it into the formula, you're going to say n, which is equal to the number of terms you want to sum up. So you'll look here to here. How many terms am I summing up? I started at 0, went to 10, that would be 11. But this one we were starting at 1. Okay? So moving on. Okay, so now listen up, this is different. So we've been dealing with finite series, meaning finite means you can see the end. So obviously we can sum it up. If we know where the series starts and we know where the series ends, we can always add up that amount of numbers, right? Well, now we're going to talk about infinite geometric series. So remember, infinite means it continues forever. We do not know the end. So for example here, we have this infinite series here. 4 plus 12 plus 36 plus 108 plus ... So this is continuing forever. It's getting larger and larger, right? Exponentially larger by what number? What are we multiplying by? R is equal to 3. So we could keep getting larger. We can multiply 108 by 3. Multiply that number by 3. And we could keep multiplying those numbers forever and ever, and it's just going to get exponentially larger and larger. Well, we could never add that up, right? Because we'll just keep adding up these really, really large numbers, right? So we cannot add those up. Does everybody understand why we can't add those up? We would just be adding forever and ever, because we can always keep multiplying each number by 3. So something like this, you can't find the sum of it. But look at this next example. This is also a continuous, it's an infinite geometric series, but let's think about this. 1 plus 1/2 plus 1/4 plus 1/8. Okay, this is getting smaller and smaller, right? What's our r in this one? It's 0.5, or multiplying by 1/2. Now you could find that by doing 1/4. You could go 1/16 divided by 1/8, that's 1/2. 1/8 divided by 1/4, that's 1/2. 1/4 divided by 1/2 is 1/2. So our r is 1/2. So really we're just getting smaller and smaller by 2. We're dividing each of these numbers by 2, right? So we know, think about exponential functions, guys. As they get really, really close to 0, right? Do they ever touch 0? No, but they get danged close, right? Closer and closer to 0. So if we kept adding this up, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, I'm going to show you in this one, plus 1, let's make it bigger, plus 1 over 32 plus 1/64 plus 1 over 1/28 plus 1 over 256. We're just getting exponentially closer and closer to 0, right? So at some point, we're pretty much adding 0 each time, right? Pretty much adding 0, pretty much adding 0, pretty much adding 0. So we can actually find the sum of this geometric series, because at some point, we're pretty much adding 0. So if you were to do this on your calculator and keep going, you're going to get closer and closer to 2. So you'll just keep adding numbers, and they're just going to get closer and closer to 2. So if you could try it, if you keep adding these at a certain point, you're going to just get closer and closer to 2, closer to 2, closer to 2, because at some point you're pretty much adding 0. Does that make sense? So you can find the sum of this geometric series. Now notice, in general, here's the rule then. Here's the rule for finding the sum of an infinite geometric series. So this is the rule you'll want to write down. So if our ratio is less than 1, just like you saw, since we were getting smaller and smaller, the ratio was multiplied by a fraction, 1/2. So if the absolute value, those signs are just the absolute values. So the absolute value of r, if that r is less than 1, then you can find the sum of an infinite series. You can find the sum, because pretty much at some point we're going to pretty much be adding 0. So you can find the sum, and they say that converges. So it's converging to a number. So no matter what number you keep adding, it's just going to get closer and closer to 2 till it's pretty much 2. Okay? So you can find the sum of an infinite geometric series if our ratio is less than 1. Now, an easier way to think of this, you guys, is are we getting smaller and smaller? Yes, so it's approaching 0, so yes, I can find the sum. But if it's getting larger and larger, if the absolute value of r is greater than or equal to 1, so if we're just getting larger and larger, think about it, there's no way to find the sum, and they say that diverges then. So you'll kind of have that memorized, because on the test it will say, does this converge or diverge? So that just means, can you find the sum? You can. It converges if r is less than 1, but it diverges and you can't find the sum if r is greater than or equal to 1. So this is the rule in general. So now I'm going to do a problem with you. Okay, any questions on this rule here?
So all we do is find r.
Yes, to know if it converges or diverges. And then in the future problems, you'll have to actually find the sum. And I'm going to talk about that in just a second. Okay, so I just wanted to point out with the 2 examples I just showed you, when we had something like this, our r was 3, so the absolute value of r was the absolute value of 3, which is 3. Is 3 greater than 1? Yes. So we can't find the sum. So can't find the sum. And it diverges. Divergent. Okay, so then looking at this one, this is our last example. Our ratio was 1/2. The absolute value of 1/2 is 1/2, and 1/2 is less than 1. So our series is getting smaller and smaller, so it's approaching 0. So we can find the sum. Can find sum, and it converges. It converges to a number. Okay, so that's how you're going to do those the next problems. Okay, now I just want to make a point so that you can work on a lot of these before I set you free. Now I didn't ask you to find the sum of that last one, so I'm going to do number, let's see. Yeah. So if you can find the sum, we know we can find the sum if our ratio is less than 1, right? Because it gets closer and closer to 0. So here's the formula for finding the sum of an infinite geometric series. Now remember, you can't find the sum for all infinite geometric series, but you can for the ones that are getting smaller and smaller, or the absolute value of r is less than 1. So here's the formula you're going to use to actually find the sum of an infinite geometric series. So we've learned 3 formulas today, and this is the last formula we'll learn for today. So here it is. But remember, you can only use it. You can only find the sum if the absolute value of r is less than 1. So write this formula down here. And then I'm going to do number 8 with you. So S is equal to A1, which just means the first term of our series, divided by 1 minus R, the common ratio. But we can only find the sum of an infinite geometric series if it's approaching 0, so if it's getting smaller and smaller. So number 8, it says determine if each infinite geometric series diverges or converges, state if the series has a sum. So looking at this one, I've got to figure out my R first. So like algebraically, you could do this by going 3/4 divided by 3/2. So you flip the second and multiply, so that would be 2/3, so to multiply by 2/3. So then 3's are gone, so we get 2/4, so that's 1/2. So R is equal to 1/2. Does everybody see how I did that algebraically? Or you could just look at it and say, I see I'm multiplying by 1/2 to get from one term to the next. So R is equal to 1/2. So then say, okay, the absolute value of 1/2, is that less than 1? Is 1/2 less than 1? Yes, so we can find the sum. It's getting smaller and smaller. So you'd say, yes, we can find the sum, and so it converges. And we're done. Now this one, notice on problems 8 through 13, that's all it asks you. But on 14 through 17, it asks you to actually find the sum. So I'm going to find the sum on this one so that you'll know how to do it real quick, and then you can finish up the problems 8 through 17. So watch how I would find the sum on this one. So our A1 in this one is what? What's our first term? 3. Very good. And then I know, okay, I can add this up. It does have a sum. So I'll use the formula. S is equal to A1 over 1 minus R. So I'm going to just plug that in. The sum is equal to A1, which is 3, divided by 1 minus, we decided the R was 1/2. So the sum of this infinite geometric series is going to be S is equal to, now be careful, we need to throw that in parentheses. So you'll have 3 divided by 1 minus 1/2 is 1/2. So 3 divided by 1/2 is 6. So the sum of this series in particular is 6. Does everybody see what I'm saying here? Okay, so this is the last formula for today. It's to find the sum of an infinite geometric series, but you can only find it if it's approaching 0, getting smaller and smaller. If not, it's getting larger and it's diverging. Okay, so now you'll do the problems 8 through 17.